Okay, so you'll need your calculator, so you can all take your calculators out. Right. So question 1 here. How much energy is required to balance this? 2H plus 2H becomes helium-3 plus a neutron plus energy. We want the energy. So, first we need to get the mass here, which would be 2 times, and I tell you what that is in the question, 2.0141 AMU. Okay? And then we need to calculate this. What's the helium one? 3.01603, is it? Plus 1.00867 AMU. Which will be bigger? This or this? First one. So, can you tell me what that minus the other one is, please? 0.0035. And Einstein said that that missing mass became energy. So according to Einstein, the energy will equal that times U c squared. Alright, so when you're ready, if you can give me that, please. Maybe Chow, you could give me this. Oh, you have it done?
5.229 times 10 to the power of negative 13.
Should we trust Chow?
Yes.
I think we should trust Chow. He doesn't trust you. No, you can double check. He won't be. Chow won't be offended if you check. Good man, Chow. All right, let's have a look at number 2 now. Right, so what have we got going on here? We have uranium 235. How much is that? 235.044 plus a neutron 1.00867. That becomes barium 138.909 plus krypton 93.9344 plus 3 neutrons. Okay, so if we can get the difference again, what have we got? Zero point 18326 U, yeah, and then times c squared. You got an answer? Thank you. Thank you. 2.735 times 10 to the minus 11 joules. B. How many moles, roughly? Oh. Oh, I gave it to you in a previous lesson. It is a constant on the calculator as well. You'll have to go back and check. Okay. You can always Google, if you just Google AMU, it might just give it to you straight away. Oh, Chow has it there for you. B. Roughly, how many moles are in a gram of uranium-235? So you know from chemistry that 1 mole will equal in mass 235 grams. Yeah? Right? Because the mass number is 235. You know, so like for example, carbon 12, a mole of it is 12 grams. Yeah? Hydrogen, what's a mole of it? 1 gram. Okay, so uranium, a mole of it is about 235 grams. Okay, so how much is 1 gram? Well, that will just be 1 divided by 235 moles. What's that there, please, Matt, as a decimal? 425, like this? Yeah, okay. Now, part C. How many nuclei are in a gram of uranium-235? Yeah. So in other words, how many uranium isotopes is in this many moles? So you know, you just multiply by Avogadro's number here. So if you multiply by Avogadro's, what, it's 6.02 times 10 to the 23 times this n here, what do you get? Ten to the 21. 10 to the 21? Yeah, okay. Now, D. If we go back to the start. Oh, I didn't write it down. You see the reaction uranium plus neutron equals barium plus krypton plus neutrons plus energy. Yeah? How many isotopes of uranium do you need for each reaction? You need 1 uranium and 1 neutron, right? So, in part D, how many reactions can you produce with 1 gram of uranium? What would the answer be? Which are we doing? D, isn't it? Yeah, D, not E, sorry, D. How many reactions can we produce? Well, it's the same as that. Because this is your number of uranium-238 isotopes, isn't it? And 1 isotope of uranium is needed for 1 reaction. So, how many reactions can you make? This many. Is that okay? Are you sure? Okay. E. Therefore, how much energy can you produce with 1 gram? Okay, so we take the answer Matt gave us earlier, which is this, and we multiply by the number of reactions we can make, and we get the total energy from 1 gram. So, yeah, Siba, you're going to give it to me, is it true?
7.001 times 10 to the 10.
Joules. Okay. F. Ireland consumes 3 gigawatts of energy, mostly in the form of fossil fuels. So in Ireland, the whole country uses 3 gigawatts. So that means every second, how many joules of energy is consumed? How big is giga? How big is mega? 6. What's 10 to the 6 called? Million. How big is giga? Billion. Billion. So every second the country of Ireland consumes 3 billion joules. Okay? Imagine you had 5 grams of uranium, which is the mass of this page. So you take 5 grams of uranium, which is the same weight as this piece of paper. It's light. Okay? How long could you use 5 grams of uranium to power Ireland? if the whole process is 51% efficient. So we have to use a couple of formulas here. We have to use our old friend power equals work over time, and also power out equals power in times efficiency, although it's written differently, I know. I had it as a fraction previously. So you have, or I could say it like this: energy out equals energy in times efficiency. So your 5 grams of uranium can make 7 times 10 to the 10 joules, but the process is 51% efficient. So do we get to use all of this? No, we get to use about half of it. What is 0.51 times 7.001? That's probably about 3.5. Yeah? Oh, this was for 1 gram, wasn't it? Oh, thank you, Matt. Yeah, and I also have to times it by 5. Thank you. So, can you multiply this number by 0.51 and then also by 5? This number multiplied by 0.51 multiplied by 5.
0.51.
Yeah. Sorry, 1 sec, Siba, sorry. Okay, go on, yeah.
1.79
Yeah.
times 10 to the 11.
Joules. Okay, so if we put that in there, this is time equals work over power, which equals 1.79 times 10 to the 11 over, what was the power required for Ireland? 3 gigawatts. 10 to the 9.
59.6.
Yeah, so in other words, 60 seconds. Basically a minute. Now think about that, please. Everybody, just think about that. You have 5 grams of uranium. That's the weight of this page. Okay? That's enough to provide, that's able to provide energy for the whole country for 1 minute. Just this much uranium. 1 minute. Impressive, right? Now, G. Note that 5 grams of crude oil can be burnt to release 225 kilojoules of energy. Again, assume 51% efficiency. How long would 5 grams of oil power Ireland? Okay, so we need to get, Siba, could you do 225,000 times 5 times 0.51? 573750. So let's do our calculation again. Time equals work over power. Zero point zero 191. So that's about 0.02. Well, no. It's about, yeah.
1 times 5.
Oh, sorry, I said 5 in the beginning, didn't I? Sorry, that's wrong. So this answer is 5 times too big. So can you divide this answer by 5? Sorry, that's wrong. I shouldn't have multiplied by the 5 here. This 5 here is wrong. Sorry. 114750. That's what the work is. Okay, thank you, Siba. And the time will be.
No, that's just, I didn't divide it by.
Yeah. So the time is 14750 divided by 3 times 10 to the 9.
3.55.
10 to the minus 13.
Minus 5.
To the minus 5. Like this. 10 to the minus 5. Well, 10 to the minus 3 is milli. 10 to the minus 6 is... So this is 0.385 times... Oh, sorry. This is 38.5 microseconds.
It's 38.25.
Oh, okay. So, 5 grams of uranium, 238, will give you 1 minute of power. 5 grams of oil will give you 38 microseconds. H, oil or nuclear? Nuclear. Three. What is the mass defect of copper 63? Okay. So, copper 63. We need to first know two things. How many protons and how many neutrons. So, using your periodic table, how many protons are in copper? It's going to be around about 30. 34. So therefore, how many protons 29, neutrons 34. Okay? So the mass should be 29 proton masses. What's a proton? I give it there, don't I? Yeah. 1.00728 plus 34 neutrons, 1.00867. That's what the mass should be. What is that number, please? AMU. That's what the mass should be. However, what the mass is I give it there 62.91367. So I can answer my question what the mass defect is. The missing mass is the difference, which is 0. 59633 AMU. Okay. B. What is the binding energy? So how do I get the binding energy here? Same as last time. M C squared. Now, before you write before we continue, we usually write this in electron volts because it's so small. So if you divide that by the E, please. So divide that by that electron charge constant. Should be big enough.
Very big.
Yeah.
5.
Oh, Chow has it in front of me. So, could we make it mega? Could we make it giga? We could definitely make it mega. So it would be 555.5 mega electron volts. All the fives. And finally, what is the energy per nucleon? So that's like it's like an average per nucleon. So how do I get that? Energy per nucleon. How many nucleons are there? Do you know what nucleons are? Oh, nucleons just mean protons or neutrons. They're the things in the nucleus. So how many nucleons are there? Yeah? 63. So what do I do? Divide by 63, yeah. 8.817 mega electron volts per nucleon. Okay? Yep. I can stop the recording.